Hello, my future engineers. How are you? Now, the CT intimations are out, and I hope that you are now more motivated, more focused for your JEE 2025. Hi, welcome everyone. Welcome to Rankplus IIT JEE English. And in this video, I'll be covering the electromagnetic induction. I'll be covering the theory previous year questions from JEE 2023 and 2024. So this session going to be very informative for you. First of all, you must know that what is our target from this lecture. So I'll be covering every part of the JEE 2025 syllabus. So if we will see the syllabus, which is our target, we can divide this chapter into 5 parts. So there are 5 parts. We will start with the Faraday's law. Second, we will do induced EMF and current. Third, we will do the Lenz law. Then after the Lenz law, we will go for the eddy current. And once we cover the eddy current, there is self-induction and the mutual inductions. I'll be covering the theory. Plus, I'll also take the questions from previous year, questions from 2023 and 2024. So this is our target in this lecture. But before we start, I want to tell you that please join our Telegram group, because on that Telegram group, you'll be getting the PDF from this session. Plus, there are so many things which you will get on our Telegram group, like the daily practice paper. And in addition to that, the information about the exams, notifications, the other exams which you must fill for like if you are aiming for 2025, right? So there are so many things which you get in our Telegram channel. So the link is in the description. Plus, I think that it's the duration of the video will be around 2 hours, 2 to 2.5 hours. Okay. Now, again, there is one information, the information about a playlist which is there on our YouTube channel, which you can follow to improve your score. There are so many lectures out there in the playlist which we have completed specifically for the JEE 2025 aspirant. Now, let me start the session. So, before we actually go from the go to the topic of electromagnetic induction, first of all, we must know that what is the magnetic flux. We have already studied the electric flux. It is similar to the electric flux. So magnetic flux means that how many number of magnetic field lines are passing through a particular area. If I'm having a particular area of cross section A, then how many number of magnetic field lines are passing through this area? How many magnetic field lines are passing through this area? To get it mathematically, if I need to find out the magnetic flux, I can write this as using a phi symbol. So magnetic flux will be equals to a dot product of B and A. I'm considering the magnetic field as a vector quantity and area also as a vector quantity. So ultimately the magnetic flux will be a scalar quantity. So we have to do the dot product, and you can write it as BA cos theta. Right. Now, if I'll like if I'll twist this surface area, I'm asking you to tell me I have twisted this area by an angle of theta. And if somebody asks you that now tell me what is the magnetic flux through this particular area, it's having a area of cross section A and the strength of magnetic field is B. Now, you must know from the concept of physics that whenever we are basically calculating the dot product refers to the like we have studied dot product multiple times in work. Also, we used to use this dot product. In dot product, basically you have to keep in your mind that both the quantities must have the same directions. Like here, I want that magnetic field and the area vector must have the same quantity. So now here, if I'll see, this magnetic field is having the this area vector. This is the area vector. So this area vector is going in this direction. I need to ensure that either this magnetic field component I have to take in this direction, or I have to consider this area vector in this magnetic field direction. So if I'm having theta here, that angle must be 90 minus theta, right? That angle must be 90 minus theta. And there, like if you take the components of this, at this side you can consider a cos 90 minus theta, and here you can consider a cos a sine 90 minus theta, and that 90 minus theta, this 90 minus theta will become cos theta. So you will get a cos theta. This is the component of this area vector towards the direction of magnetic field, and we have the magnetic field here, right? So if we multiply both these quantities, I'll get AB cos theta. So this is what you will get, right? I hope that you understand. If you have any doubt, then please do let me know in the chat. Is it clear, my dear? Similarly, if the same scenario, I'm having a particular area twisted by an angle theta. Now this time, I am considering the angle from here. I'm saying that this is alpha. Okay, this is alpha, and the magnetic field lines are going in this direction. Magnetic field lines are going in this direction, and now you have to get the value of magnetic flux. So how you gonna find? I told you that whenever we are doing the dot product, you have to ensure, this is the basic principle. Whenever we have to find out the dot product, the direction of both the quantities must be same. This thing you have to ensure. So this is what I am saying here. So I have to resolve this vector, right? I have to resolve this vector. I can resolve this vector in, if I'll resolve this vector this side, I'll get a cos theta. And if I'll resolve this vector at this side, I'll get a sine theta, right? So using this, I can get AB sine theta, AB sine alpha. As we are taking alpha, so I'll use alpha here. So it A cos alpha, A sine alpha. Here you will get A B sine alpha, and here you are getting AB cos theta. I hope that you will not be stuck with this formula, that for this quantity you have to consider cos theta. Basically, it depends that from where we have to take the angle, right? It particularly depends that from where the angle is given to us and from where we are considering in our calculations. I hope that this scenario is clear to you. Is it clear, my dear? Kirtika Kejia. Okay. What's your real name, Kirtika? Nanny? Luffy? I hope that this pattern is clear, right? Now, let's solve some questions related to this pattern. So, we have this question. In this, a plane of coil of area, so area is given to us, having 50 turns, is perpendicular to the magnetic field of 3 into 10 to the power of minus 5 Weber per meter square. Okay, so magnetic field value is given to us. The magnetic flux linked with the coil will be, so we have to find out the magnetic field here, magnetic flux. So magnetic flux is equals to BA, right? And cos theta. See, in this condition, it's given that the plane of a coil of area and having 50 turns is perpendicular to the magnetic field. So I'll consider this as my area vector. Okay. And now this is saying this is the plane of the coil. Okay. This is the plane of the coil. I'm considering this as my coil. Okay. If this is a coil and I'm placing this coil on this plane. This is my plane. I'm having a coil. This is my plane. Now, the magnetic field. See, read the question carefully because in multiple scenarios, we do not even have to do the calculation. It might possible that we will get the zero answer, right? So, reading the question is very, very important. If you find that zero option is available, so in this question, a plane of a coil of area 1 meter square and having 50 turns is perpendicular to the magnetic field of this much. So basically, it's saying that plane of the coil, that means this coil, this is a coil plane, right? This is perpendicular to the magnetic field. So if I am having the magnetic field direction going through this, I can consider that my magnetic fields are going like this. Are you getting? So in this scenario, can you say that your phi is 0 degree? Your phi is 0 degree. Magnetic field is perpendicular, but perpendicular to what? Perpendicular to the plane of the coil, right? But with the area vector, it is making an angle of 0 degree. So I can say that be a cos 0 degree. Plus, if I'm having number of turns, I'll place n before my formula. So for like now you just have to do the calculation. 3 into 10 to the power minus 5. Area is 1. This is 1. So phi b is equals to 1.5 multiplied by 10 to the power minus 3 Weber. Are you getting the same answer? Are you getting the same answer? Shall we move forward? I hope that this is clear. Kirtika? My real name is okay. Kirtika Kejia. So you were there in another channel's live sessions as well, right? At the time we got the CT intimation. Where are you from? Now let's move to the next question. Yes. Now this is question number 2. Question number 1. Question number 2. Circular coil of 100 turns and radius 2 centimeter. Now see, remember one thing, that whenever you are doing the calculation related to the physics, you have to remember that you have studied from Manoj Kumar sir. You have to remember that you have studied from Manoj Kumar sir, and you have to follow me. Follow me for the units. Your length must be in meter. Your length must be in meter. Your weight must be in kg. Your time must be in seconds. Right? This you have to follow. Now in this scenario, I'm having radius as 2 centimeter. I'll take this as 2 into 10 to the power of minus 2 meter. You can keep this in your mind, because when we are solving these types of questions in the real exams, this is not what we will do, or this is not what I will suggest you to do, right? Because we have to save our time, because saving time is very important. It will help you to solve another question. If you are able to solve 2 or 3 extra questions, it will ultimately result into 8 to 12 marks higher as compared to your competitor. And this is basically the make it or break it situation. So in this, we have a circular coil of 100 tons and radius 2 centimeter is placed in uniform magnetic field. Magnetic field is also given to us, which makes an angle 60 degree. See, which makes an angle 60 degree. This is very important because here we get to know that from where we have to consider the angle. So here the angle of 60 degree with the direction of field, then find the flux flowing, find the flux passing through this coil. Okay. Now I'm considering that if I'm having a coil and there are 100 number of turns in this coil, the number of turns is 100. Okay, radius is also given to us. Radius is 2 into 10 to the power of minus 2 meter. We do not require radius. Basically, we have to find out the area. So area you can find out. Area is pi r square. So you can write 4 into 10 to the power of minus 4. Okay, because area is pi r square. So this is what we will get if we find out the area. And we know that area vector is basically perpendicular to the next. We have to consider that, okay, now is placed in a uniform magnetic field. B is equals to 2 Tesla, which makes an angle 60 degree with the direction of the field. Okay. Circular coil of 100 ton and radius is placed in uniform magnetic field, which makes an angle of 60 degree with the direction of field. So this is my magnetic field, which have the value of 2 Tesla, and the angle we have here is 60 degree. Now tell me what must be our answer to get. Tell me. Nice trick, MKS. Huh. Tell me which angle will you take? Theta. Find out. Tell me. Tell me. See, if I need to find out, I already told you that we have to keep the direction of B and A in the same direction. Okay, the direction of area and magnetic field must be in the same directions. So I can do one thing. Either I'll take this component at this side, or circular coil of placed with the magnetic field B, which makes an angle of 60 degree with the direction of the field. No, 60 degree is given from here, this side. 60 degree is given from this side. So this will become 30 degree. And if I need to calculate phi, I have to do BA cos 30 degree. My magnetic field value is 2. Area is pi. 4 multiplied by 2 to the power minus 4. And cos 30 degree is root 3 by 2. So you will get 4 root 3 pi into 10 to the power of minus 4. So this is what you will get as an answer. Is this what you are getting? Tell me. Yes, number of turns you have to take. Number of turns is also there. So multiply it by 100. So if you multiply this by 100, you will not be there. This is what you will get. Okay. Ishika, Radia, I hope that this thing is clear. Now, once we are done, Now, once we are done with this magnetic flux, we can move towards the experiment, the very popular experiment by Faraday and Henry. There are simulations for this experiment. If you haven't done it, I would suggest you that you can search PH80 simulation of Faraday experiment. There you will get, like, you can search on Google PH80 simulation for Faraday's law. Okay, if you search for that PH80 simulation for Faraday's law, you will land up to a web page where you will see that these experiments are there and you can do it practically. So in the first experiment, I'll tell you what he had done. Faraday. There was a coil. There was a coil like this. I'm having a coil here, right? This coil is connected with a galvanometer. Why galvanometer? We are taking a galvanometer. Galvanometer is a very sensitive device which can detect a very feeble current. So if there is current, there will be a movement in the galvanometer. Okay. So I'm having a coil like this. I'm having a coil like this. If I'll do one thing, I'll take a magnet which consists of North Pole and South Pole, and I'm bringing the magnet near to this coil. I'll see a fluctuation in the galvanometer. This fluctuation remains there when I'm moving it. If I'll be still, if I'll keep this magnet at rest, then there is no deflection. Even if I'll keep this magnet inside the coil, there is no fluctuation at all in the galvanometer. But the moment I started moving it, there is fluctuation in the galvanometer. And the direction of galvanometer is also different. When I am moving it in the forward direction, it will give me one side direction, and when I'm moving it out, it will give me another direction. So Faraday think about this experiment, and he thought that basically the current, when if the galvanometer is moving, that means there is current, right? So magnet just by moving the magnet, we can produce the electric current. But why current is produced here? When we are moving the magnet, basically we are moving the magnetic field. And when we are moving the magnetic field, the magnetic lines associated with that magnet will ultimately result into change in magnetic flux, right? Is it clear, my dear? Right? So this is what thought by Faraday. He thought that when something is moving, then there will be the induction, and due to that induction there will be a generation of voltage, and if the circuit is completely closed, then there will be a flow of current also. Now similarly here we have our limitations. Why? Because we know that permanent magnet have a specific magnetic field. We cannot increase the magnetic field strength of the magnet, right? We can do it using the spatial coil. If in a spatial coil I'm placing, like, this is a coil I'm having, and I'm attaching this coil with a battery I can choose as per my requirement. And we know that if the current is flowing in a battery, there will be a induction, there will be the generation of magnetic field, magnetic strength will be there. And if I now move again, similar kind of observation was observed, that galvanometer starts moving. Now there is a question in NCRT, solved example, that what you are asking, cheat sheet I'll share. Do not be worried about, I'll share the cheat sheet. Okay. There is some modification I have to do. There are some chapters which is left. So after updating that, I will upload. Okay. This is like cheat sheet is for you only, guys, right? Now, what I was telling you, I told you that there are two experiments. The first experiment, we have the limitations of the permanent magnet. Here we got we can increase the number of turns. If we increase the number of turns, the magnetic field can be increased. We can increase the voltage, the magnetic field strength can be increased. So we can do better experiment at this side, right? So right, I was telling you that if galvanometer was not there, because galvanometer is a very sensitive device that can detect a very feeble current. So I'm saying that if galvanometer is not available to us, then what is the best substitute which we can take? right? If I have to do this experiment and I do not have the galvanometer with me, then can I do this experiment? I have the magnets with me, I have a coil. Yes, I can. What I need to do is I have to take a very small wattage bulb. If I'll connect a very small wattage bulb, then what will happen? If I move this magnet, the bulb will glow. If I'll continue moving this magnet, the bulb will keep glowing, right? But the moment I stop the movement of the magnet, the bulb will stop glowing. Similarly, once these two experiments are over, Faraday was in a mood to give a law which states that there will be an induction of induction is basically depends on that you are being influenced by another object, right? So Faraday was in a mind that there must be a law that to induced current in another coil, we must move the magnetic field, right? But later on, when he was going to give this law, suddenly he realized that if he do not move, he do not move this coil or a bar magnet here. Here we are having a bar magnet. In experiment 1, we are having a bar magnet. Here we are having a coil. We can change the number of turns, we can change the voltage to increase or decrease the magnetic field. So in this third experiment, what he had done is just switching on the key on and off also results into the deflection in galvanometer. Now in this third experiment, we do not require the movement. We do not require a relative motion between the coil and between these two coils, C1 and C2. Because according to this first and second experiment, relative motion is required. What is relative motion? Relative motion means that either I'll keep this coil 1 at rest and I'll keep moving this bar magnet, or I can do I can do the vice versa also. I'll keep this bar magnet as at rest. I can move this coil. Also, I can do one thing. I'll keep this coil 1 at rest and I can move this coil 2. Or I can do one thing. I'll keep this coil 2 at rest and I can move this coil 1, right? So both these experiments require the relative motion, right? So Faraday is in the mood that he will be writing the law. But suddenly he also observed. Scientists are very good observer. They do the observation and then they give fancy jargons name to the phenomena what they have observed. So this is what you are getting here. So in the third experiment, he observed that the movement is not required. There is no relative movement here. Just by switching on or off a key, you are getting a deflection here. Okay. Just by switching on or off, you are getting the deflection here. So ultimately, he has to give some laws, right? So after observing all these three experiments, he came out with a law. The law states, this is known as Faraday's law. The first law states that a changing magnetic flux, see here, a changing magnetic flux through a conductor induces an EMF. The word changing is very important. Changing means we do not want a static thing, right? Static magnetic field is not required, because I told you that if I am having a coil and even if I am having the like very strong bar magnet and I am keeping this bar magnet here, it won't be generating any current. But the moment I started moving it, the moment I started moving the bar magnet, the current will be there, right? I hope that this thing is clear. Vishnu? Now, now this is the first law. The second law states that now in the first law they are saying that if there is changing magnetic field, there will be an induced EMF. In the second law, basically he tells about that what is the magnitude of that induced EMF. So the magnitude of induced EMF, he told that it is equivalent to the rate of change of flux. He told us that it is equal to the rate of change of magnetic flux. But later on, we got to know that he told that what is the magnitude of the EMF, but he didn't tell us about that what is the direction of the induced EMF. EMF is nothing but the voltage generated, right? So he do not tell us that which side will be positive or which side will be negative. So it is given by the lens. So we have a modified, or I can say that lens, Faraday lens law. It is better to say that we have Faraday lens law, and we will use Faraday lens law in our equation. So Faraday lens law is EMF is equals to minus of d phi by dt. This minus sign basically represents the direction of induced EMF. The induced EMF will be generated in the direction in which basically it is opposing the rate, opposing the change of flux variation, right? So Lenz's law is basically depending upon the conservation of energy that you have to remember. Now, if in any situation you are seeing that there is a differentiation or there is a rate change, I can assume one thing, that if you are very good student, you must know that there will be a pattern of questions which might come from here, right? The pattern is that you might get a equation of the flux similar to like if I'm giving you 5t cube plus 3t square plus 6. This is flux given to us. Now, if somebody asks you that what is the EMF generated, right? If somebody asks you what is the EMF generated, you have to differentiate it minus d phi by dt, and you will get 15t square plus 6t. This is what you will get. Now, if like the question will tell you that at what point, at what time you have to find out the EMF. So if you have to find out EMF at t is equal to 3 second, so you have to put time as 3 second here in this equation. You will get EMF is equals to minus 15 into 9 plus 6 into 3. Okay, so this is what you will get. Now if you multiply this thing, what you will get, 135 and 18. Please do the calculation on your own. Is it the answer which you are getting? Please do let me know. Is this is the answer which you are getting? Is it clear, my dear? Okay. Now let's see. I hope that this point is clear to you. Is both the experiments, all the experiments, there are three. There were three experiments. All the experiments and this law is clear. Please do let me know in the chat. Please do let me know in the chat. Anish Giri. Great to know that, Anish. Cheat sheet, Kirtika, Luffy, Nanny. Tomorrow in the morning we have a mock test in which I'll be taking 25 question. Later on in the evening, I'm planning to take another session on alternating current. Okay, so I was in a mood to take EMI and AC together, but later on I got to know that Nabamita ma'am is also taking a session, and she is taking a long session. So I thought that it will be nice to give you some rest. So I sacrificed my time. So I took on. I'm taking only all electromagnetic induction. So is it clear, my dear? Is it clear, my dear, till now? Is this clear? Now let's move to the another part. Now this question is from JEE 2024, 31st Jan shift 2. Earlier the exam was started on 27th of January. This time there is like this shift is starting from 22nd of January, right? So this is the question which you have. We have been provided by phi. You have to find out the induced current. Tell me, if I need to find out the induced current here, what is induced current? You have to think in terms of the formula only. Induced current we can apply the Ohm's law. What does Ohm's law said? V by R. So here I can keep EMF divided by R. And for this EMF, you have to use that EMF is equals to minus of d phi by dt. Right? So use it and solve it. And do let me know that what is the answer you are getting. Please, everything is given in the question, and I have already told you that how to approach this. Within few seconds, I hope that now you are able to solve it. Anish, Kirtika, tell me. Tell me, guys. You have to be fast. You have to be fast. You are an engineer. You tell me. So, if you are not able to solve it, let me solve this question. I hope that you are not giving the answer due to the time lag, not due to the concept. So, if I have to find out phi, it will be minus. I'm doing the differentiation here. It will become 10t minus of 36. Put t as 2 seconds. So, EMF you will get 20 minus of 36. 16. So I is equal to 16 by 8, 2 ampere. So you can put 2 ampere here. Is it clear, my dear? 31st Jan shift to 2 ampere is the correct answer. Now, first of all, let us learn that how to find out direction due to Lenz's law. As we know that, the EMF direction will be in the opposite direction. So now let me consider a very easy peasy. If there is a coil, if I am having a coil like this, and there is a north pole, this north pole is moving toward this, then what will be the direction of induced EMF in this coil? You have to tell me. Now, to oppose the motion, of this magnetic bar, there must be a induced current which will give rise to the north pole in this loop. And if I have to generate a north pole in this loop, the direction of magnetic field, the direction of the current, induced current, will be in what direction? Anti-clockwise. If I'll see from here, if a person sees from here, he sees that the anti-clockwise, current is induced. Okay. Also, if a person is standing at this side, he will say that a clockwise current is induced. And ultimately you have the magnetic field line. You have the magnetic field lines look like this. It is going from this side to this side. Are you getting this? This is due to the induced current. And we know that it will be like that this will become a north pole. So from north pole, the magnetic field lines are going outward, and in the south pole, the magnetic field lines goes inward. So this is what we will get. I hope that this is clear to you. Now, opposite. Okay, now if I move this magnet, if I move this bar magnet away from this coil, then what will happen? If I'm moving this magnet, if I'm moving away this magnet, the induced current must be in this what direction, so that this coil will attract this magnet. See, listen it. Now, if I'm moving this bar magnet away from this coil, the induced current in this coil must be in such a way that it will now start attracting this bar magnet, and it will slow down the movement of this bar magnet towards the direction in which it's moving. See, in the first part, the bar magnet is moving from left to right. So the induced current is in the direction in which it can basically slow down the movement of this bar magnet. Similarly here, now the bar magnet is moving from right to left, so the direction must be in such a way that it will slow down. So how you can slow down? If this is a north pole, you have to create a south pole here, because if you create a south pole, then there will be an attraction, right? So that is my induced current. And if a person sees from this side, he will see that there is a clockwise direction, there is a clockwise current. Clockwise current is induced. Okay. Now, if a person sees from this side, if a person sees from this side, we will say that an anti-clockwise current is induced. I hope that this thing is clear. If I have to draw the magnetic field lines in this scenario, it will be, because this side is south pole and this side will be a north pole. Here I'm having this side as north pole and this side as a south pole. Now the direction of magnetic field lines will be I hope that both the examples are clear. Is it clear? Abhinav Kumar, hello. Vision, Kirtika Kezia, is it clear? I hope that this thing is clear. Now, let's move to the another part. Direction of induced current. Now moving forward, we have to find out the direction of induced current. Now the third example is, I'm having a constant current flowing from left to right. There is a constant current, and I'm having a loop here, and you have to find out that what is the induced current. Okay, you have to find out that what is the induced current here. Make it little bit challenging, I'm considering two loops. If current is increasing, then you have to find out that what is the direction of induced current in both the loops. If current is decreasing, then also you have to tell me that what is the direction of the induced current in both the loops. Tell me, what is the induced current direction in the first case when the current is constant? When the current is constant, as we know that due to the constant current, there will be a magnetic field at this point and this point. If I need to find out the direction of the magnetic field, I can use the right hand thumb rule. Using the right hand thumb rule, I know that there is a very simple rule. You can remember a very shortcut, a very short form. I use generally this thing. This is known as relo. Relo means if you are considering a current carrying conductor, if you are thinking that you are holding a current carrying conductor, you can apply this rule. You have to keep your thumb in the direction of the current, then your right side will be having the inside magnetic field, and your left side will be having the outside magnetic field. So now here I'm saying that right side you have inside, and left side you have outside magnetic field. Okay, right side inside, left side outside. So you an inside magnetic field is shown by cross, outside magnetic field is shown by dot. So here I'm having cross, here I'm having dot. But you also know that these area are constant, right? Magnetic fields are also constant because when the current is not changing, the area is like we have the constant area, we have the constant magnetic field. And if somebody asks us that what is the magnetic field, so we have ba cos theta, right? And if somebody is asking that what is the emf is d phi by dt. Now we know that d phi is not changing, so if they are not changing, the induced emf will be 0. So there is no induced current. There is no induced current. The induced current will be 0 in this scenario. The induced current is 0 in this scenario. Now moving here, if I know that my current is increasing, so if my current is increasing, then how you will find out the direction of induced current. To find out the direction of induced current, we will be applying the Lenz law. And Lenz law says that the direction of induced EMF must be in the direction in which it is basically opposing the cause. So we know that here my current is increasing to oppose this. And if the current is increasing, what will be the direction of magnetic field? Here there will be dot, here like here there will be cross, here we are having dot. So I'm saying that we are having a dot, and this dot is basically increasing. So I need to decrease this dot. To decrease this dot, what I have to do is there must be a current flowing in this direction, right? If current flows in this direction, I'll have the magnetic field at this point going downward. So this is how I can reduce it. Similarly here, basically we are getting the cross here. So I need to generate a current which will help me to get a dot field. I'll explain you here. If you didn't get, not an issue, because first time hardly anyone gets the gist of this. So I'm considering that we are having a table here. And if I'm having a table, there is a current carrying conductor. I'm having a table and I'm having a current carrying conductor. I'm considering that there is a loop. And in this loop, due to this current carrying conductor, the magnetic field is going upward. Right? The magnetic field is going upward because we know that this will be cross and here we will be getting dot. And sooner or later, as we know that this current is increasing, so if this current is increasing, this magnetic field will be increasing continuously, right? We know that magnetic field basically depends directly depending upon the current. So if I'm increasing the current, my magnetic field strength will also increase. But according to Lenz law, area we have, like area is constant, so magnetic field is increasing. So according to the Lenz law, we have to, like the induced current must be in the direction in which it will be opposing the cause. So what is the cause of the change in flux is the magnetic field. So induction will happen in such a way that it will reduce the magnetic field. So I want that my magnetic field will be induced in the opposite direction. And to get the magnetic field in this direction, you have to produce a current in a anti-clockwise direction or a clockwise direction. So here we are getting a clockwise direction, here we are getting an anti-clockwise direction. I hope that now this is clear to you. Similarly, if I'll go there, now here, the current is decreasing. So if the current is decreasing, the normal magnetic field is cross at this side and dot it at this side. When you are losing, everyone will be there to help you, to assist you, right? When you are losing, everyone will be there to help you to get you more motivated. So this is what I am doing here to motivate you. So now I'm telling you that when the current is decreasing, these magnetic fields are also decreasing. Now I have to support this magnetic field because these magnetic fields are continuously decreasing, right? So to increase this magnetic field strength, what I have to do is I need to create the current in such a manner that it will help the in this magnetic field. So in this scenario, I want that this will become a clockwise current, and this will become anti-clockwise. I hope that this scenario is clear to you. Is it clear, my dear? Is it clear? Is the third example clear to you? Please do let me know. Kirtika, Abhinav, Anish Giri, is it clear? These are very, very important. These are very, very important. Now, let's move. Let's move toward the next part. In the next part, let me consider that there is a table. Okay. Now, if I'm putting a cross here, it means that the magnetic fields are going inside. And now, if I'm having a loop here, this loop is moving in this direction with the velocity v. You have to tell me that what is the induced current in this. Then it's moving in this direction. This is position A. This is position B. And this is position C. You have to tell me that what is the direction of the induced EMF in position A, B, and C. Right? You have to identify that what is the direction, what is the induced current direction in case of A, B, and C. This is what you have to do. Now, if I apply the rule here, I have to think in terms of formula. We know that phi flux is basically depending upon BA and the cos theta, right? When you have to do the, when you have to calculate the EMF, it will be d phi by dt. That means you have to differentiate this, right? Now, I'm saying that if this object is moving, if this object is moving in this direction, I have the magnetic field as constant. This magnetic field is constant, right? I'm having a constant magnetic field. And I'm saying that this area is moving in this direction. So what is happening here? Basically, the area is increasing. If I'm having a circular loop here and I'm moving this circular loop in a area where there is a magnetic field, if I'm placing this cross here, it means that the magnetic field is going downward. If there is cross, it means that the magnetic field is going in the downward direction. And how we can get this? By keeping a north pole at this side and keeping a south pole below the table, right? So using this, I can say that the magnetic field will be moving in this direction. This is how basically we generate the magnetic field. We have like we have the shoe magnet, right? And if you like again forcibly move those magnets, you will get this type of magnet. Now, if I'm having north pole at the top of the table and south pole at below the table, I'll be having this kind of magnetic field. So in scenario A, in situation A, I'm saying, see, this object is moving in this direction. I know that area is increasing because earlier very small part is inside the very small part is inside the magnetic field, and when it moves in this direction, this area will increase, and if this area will increase, magnetic field is basically we will have more magnetic field strength. Ultimately I can say that my phi is increasing, so the more number of magnetic field lines is going inside, so the current will induced in such a direction that it will oppose it. And to oppose it, I would be saying, because the magnetic fields are going in inside, so my current must flow in this direction, so that there will be an opposite magnetic field. Okay, so in this A side I'll be having the anti-clockwise induced current. Are you getting it? Anti-clockwise induced current, because the moment it will start moving in this, there will be an increase in the magnetic field which is going downward, and he has to perform in such a way so that these increasing magnetic field will be opposed. And how he can oppose the increasing magnetic field which is going in the inside? It can oppose it by flowing a current in the anti-clockwise direction, so that the induced magnetic field in this coil, due to this current, due to this induced current, will be in the opposite direction. I hope that this thing is clear to you. Now at the position B, what will be the induced current direction? Now here also you have to think in terms of the values which I'm telling you. Like, I'm having a B here, so I'm having a particular area. This area is fixed, magnetic field is fixed, my area is fixed, my magnetic field is fixed, and I know that now my flux is also fixed. If magnetic field is fixed, if area is fixed, that means that my flux is also fixed. So if flux is fixed, you can say that there is no induced current, because the rate of change of flux, or you can say simply the change in flux will be zero. And if change in flux is zero, I can say that there is no induced current. There is no induced current. Now let's move to the last part. Last part is here. Now we are moving out of this area. If I am moving out of this area, what will happen? What will happen if I'm moving out of this area? Now the now we have to produce, like, the magnetic field will be decreasing, right? The flux will be decreasing. Now the current must be moving in such a direction that it will increase the magnetic flux. And how you can improve the magnetic flux, that too in the downward direction, uh, by generating a current in clockwise direction. I hope that you all knows Maxwell right hand thumb rule, right? A anti-clockwise. So if this thing is clear, I hope that now you can handle multiple questions. There are questions in which they would say that there is a coil and electron is moving, alpha particle is moving. Just think in terms of current. If negative charge is moving, that means the current direction is in the opposite direction, right? If alpha particle is moving, that means the current direction is in the same directions. Just you have to think in terms of what you have studied. Questions might come in any form, but you have to stick to the rules, to the principles which I am telling you. That is very, very important. You have to be very concise. You have to think that which formula, which concept we can use to solve these types of questions. And I have seen the students who remain concise while solving the questions are very good in solving the unknown problems. Right? Now, let's move to the next part of our questions. So this question was asked in JEE 2023, 6th April shift 1. The question was that the induced EMF can be produced in a coil by moving the coil with uniform speed inside a uniform magnetic field. Okay. Moving the coil with non-uniform speed inside uniform magnetic field. Okay. Now, rotating the coil inside the uniform magnetic field. I know that one thing is fixed. If I'm rotating the coil, there will be a generation of EMF. Changing the area of the coil inside the uniform magnetic field. So yes, if I'll change the area, there will be a change in the flux, because I am I'm a teacher who will teach you that you have to think in terms of formula. So formula is BA cos theta. So I am saying that if they are saying that we have the uniform magnetic field, it means that they are saying that this value is fixed. So if this value is fixed, and you know that you have to also calculate d phi. Why d phi? Because we know that EMF is equals to d phi by dt, right? So you have to think in these terms. So now, when they are saying that this we have uniform magnetic field, okay, but they are saying that you are rotating the coil. So when you are rotating the coil, you are changing this. When you are rotating something, you are changing the angle. So when angle is changed, we know that flux will be changed, and when flux is changed, there will be an induced EMF. In the D part, they are saying that changing the area of the coil. So in the second part, we are saying that we are changing the area. So if area is changed, the flux will be changed, and if flux is changed, there will be a induced EMF. So in both the scenarios, there are induced EMF. Now, the problem is that how we can remove those. Like, I can mark that my answer is this if I know, right? But also I have to prove that these two options are wrong. How? Moving the coil with uniform speed inside a uniform magnetic field. Now, if you are saying that you are moving with a uniform speed, consider this option. I'm saying that this is moving with a uniform speed, right? Uniform speed v, and there is a uniform magnetic field inside. Why there is no induced current? Because we know that phi is same, magnetic field is same, area is same, angle is same. We are not changing anything. If we are not changing anything, that means that phi is constant, and if phi is constant, I can say that d phi will be 0, and if d phi is 0, d phi by dt, that is the EMF, will also be 0. So in that scenario, I can say that this is a particularly wrong question, right? In that scenario, I can say that my phi will be a constant value, and if phi is constant, if you need to find out EMF, that will be d phi by dt, it will be 0. In the second part, moving the coil with non-uniform speed inside uniform magnetic field, what will happen if, like, it do not depends upon the speed. If it is moving with uniform speed or non-uniform speed, it doesn't matter. Basically, the thing what matters is, does anything change in the magnetic field? Does anything change in the area? Does anything change in the angle? So for both of these, we can say that it can't be our answer. I hope that this question is clear to you. See, whenever you are solving the previous year question, the questions are not important for us. What is important for us, that what are the topics which was asked in JEE PYQs and how they have framed the question, because that gives us the information that how examiner can frame a question from a very simple topic. Is it clear, Sahiti? Yeah, I'll share with you that. Surely I'll share. I hope that this thing is clear. Now, let's move toward the next part. As I told you that according to Faraday's Lens law, According to Faraday's Lens law, EMF is equals to minus of d phi by dt. Right? EMF is equals to minus of d phi by dt. And once this is clear to you, you can extend this scenario to the motional EMF. There are two scenarios in motional EMF. Like I can consider see, if I am having a rod of length L, this rod is moving with velocity v. Okay. And there is a magnetic field also. Which is perpendicular to this rod. Then there will be an EMF which is equals to BLV sine theta. EMF is equals to BLV sine theta. This is very, very important formula which you will get, right? So EMF, one part is this one, second part is this one. You have to keep this thing in your mind. Is it clear, my dear? Next, another pattern is that if I'm having a rod, I'll take, I'll draw a better diagram for this. Okay, now I'm considering that there is a length of L, okay, and this is particularly rotating with an angular speed of omega, and there is a magnetic field also. So in this scenario, we can say in this scenario, I can say that EMF, induced EMF in this wire between these two ends, this and this, will be equals to BL square omega divided by 2. So this formula is very important. This is when we are rotating. This is when we have a translational motion. So both of these formulas are very, very important, right? I hope that this thing is clear to you. Other than that, once we are done with finding out the induced EMF, we can easily calculate the current, right? If anyone asks you that what is the value of current, if someone asks you that what is the value of current, induced current especially, so induced current is equals to EMF divided by R. If I'm having a closed circuit and that circuit consists of the resistance R, my induced current will be EMF divided by R. Is it clear, my dear? Hello, ST2717. Very good name you are having. Where are you from? Now, there might be a question based on power. If you need to find out power, what is power? Power is VI, right? Power is what? VI. And you can write this thing as EI. So EMF is this thing. So you can write this thing as E square by R. Can you? See, there are so many things which you can easily find out. And if somebody asks you that, tell me that what is the energy? So energy is power into time. So you can replace this E square time divided by R. Okay. Now I think that this is done. Now let's move towards the real question from the JEE exam. So here you are having a question. Try to solve this question. Let me give you, this question is from the January attempt, 1st Feb shift 1. I'll start a timer. I think 1.5 minutes is sufficient to solve this question. PCM marathon video. Yeah, I remember. Solve this. Finished. Find out. Only few seconds are left. 18 seconds. None of you have given the correct answer. So did you find this question difficult? That's why I'm not getting the answer, or you want more time? I think I have already given you I have already given you 1 minute 20 second 30 seconds, right? So let me first explain you the question, then I'll give you some hint. If required, I'll provide you some more time, right? So in this question, we have a rectangular loop of side 12 into 5. Okay, let me draw the diagram. So there is a rectangular loop. The loop value is 12 centimeter and 5 centimeter. With its side parallel to the x-axis and y-axis respectively. Okay, opposite. This is x-axis parallel to this and y-axis parallel to this. Right? Side 12 centimeter with its side parallel to x-axis. So 12 centimeter is parallel to the x-axis and 5 centimeter is parallel to the, this 5 centimeter is basically parallel to the y-axis. So this is parallel to the y-axis. And this is particularly moving with a speed of 5 centimeter per second. This complete component is moving in the positive x-axis. Okay, so that's why I have taken this as the direction. In a space containing a variable magnetic field, so I am having a variable magnetic field here, so there must be the formula for the magnetic field in the positive z direction. Okay, so if this is x, this is y, the direction of the z positive z will be on the top of the loop, this loop. The field has a gradient of 10 to the power of minus 3 Tesla per centimeter along the negative x direction, and it is decreasing with time at the rate of 10 to the power of minus 3 Tesla per second. Okay, so basically you have to think in terms of like using the unit. You can easily find out at what they are saying. Sometimes it seems to be very difficult to identify that what they are saying. See, if you have studied physics very hard or you are good at physics, you must know some very common terms which are there, like a gradient. When I am using a gradient, it means that I am dividing any particular quantity with the length, right? So this is what we have been provided, that the field has a gradient of 10 to the power of minus 3 Tesla. That means we have been provided that dB by dx is equals to 10 to the power of minus 3 Tesla per centimeter. This x is the distance along the negative x direction, and it is decreasing with the time. And in this scenario, we have been provided that how the value of this magnetic field is decreasing. So we are provided by dB by dt. So if there is dB by dt, it's also having the same value, 10 to the power minus of 3 Tesla per second. But this, okay. Now, if the resistance is also provided to you, that the resistance is this much, and you have to find out that the power dissipated by the loop as the heat is what? Now, here I told you that to get the power, basically you have to find out EMF square divided by R. So this formula, if I'll use that, my power is equals to EMF square divided by R. Now the problem is that we know that what is the value of 6, that what is the value of R is provided to us, but we have to calculate the EMF. And to get the value of EMF, you have to do the work. Basically, this is what we have to do. Is it clear, my dear? Is it clear, my dear? Hmm. Gradient is changing field upon the distance. Yes. See, gradient is a common term. Whenever you find out the gradient, it basically denotes that we are dividing it by the length. Whenever you see the moment is also a basic term in physics. Whenever I am using the moment, you have to multiply it by the length. It could be the pure like length power is 1, length power 2. That means we can also multiply the area. Right? Now, we know that the formula to get the, like I told you, the best students are the one who think in a very concise manner and plus also uses their logic. So I told you that we have these three formulas only for the EMF. We have only these three formulas for the EMF, right? BL square omega divided by 2. This is for the rotational part, this is for the motional part, and this is a general value. So here I know that this loop is basically moving, right? The speed is provided to us, so this loop is basically moving. So I can use this formula. How many of you agree that I have to use this formula? Can you agree? First of all, you have to identify that which formula I have to use, because there are so many formulas out there, and you must be very well acquainted like in which what situation you have to use what formula. I have seen multiple times the student faces this issue that they are not able to identify that here we have to use this formula. So I'm telling you that only three formulas are there for getting the EMF, right? We know that function is not provided to us, phi function is not there. We also know that there is no rotation at all, so I can't use this. Only one which is left is this one. And also I know that here we are getting the movement, right? So if I'm getting a movement here, I can use this formula. Is this thing clear? Tell me, is this thing clear? Right? Now, if this thing is clear, you can use EMF is equals to BLV. You have to find out the answers. See, length is this, what I can take. Velocity is this, which I will take. And each and everything must be in SI unit. Okay, so length I can take 5 into 10 to the power of minus 2 meter. Velocity I can take 5 into 10 to the power of minus 2 meter per second. Now, how I can identify? Now, basically, I need to find out the magnetic field as well. Right? Without magnetic field, I won't be able to solve it. So tell me, what magnetic field value you have to take? Because without magnetic field, we won't be able to do it, right? Tell me how we can find out the magnetic field. Do anyone knows how we can find out the magnetic field? See, in this complete scenario, I need to find out that what is the magnetic field here. And we have been provided by this formula. So if I'm providing, like L is already given to you, me, I can replace this 5 into 10 to the power minus 2. Velocity is given to me 5 into 10 to the power of minus 2. Okay. So these values are given. Now I am concerned with this, that what must be the value of this one. So I can do dB is equals to 10 to the power of minus 3 Tesla per centimeter divided by 10 की power minus 2 meter Tesla per meter dB by dx. So dB is equals to 10 to the power of minus 1 dx. If you integrate this, we'll get x to the power like x by 10, right? And what is x here? X is 12. X is here what? X is 12. Because ultimately you have to pass out this 12 centimeter, right? So you can put 12 into 10 to the power of minus 2 divided by 10. Now solve it. 5 2 2 6 6 5 is 30. 1 2 3 4 5 6. Now for power, you have to square this 900. 6 into 10 to the power of minus 3 ohms. Okay. So power is equals to 150 into 10 to the power of minus 9 watt. So your answer must be 150. Are you getting? Tell me, how many of you are getting 150? Subtract B from B naught. Huh? What are you saying? What's subtracting B from B naught? What are you saying? For field 150. Gradient is changing of field of charges. Yes, subtract for field. That was earlier thing you asked before solving. Okay. I hope that this thing is clear. Is this thing clear, my dear? Okay. Now we can move forward. There, like, you can ask me one thing, that what is the usage of this thing? That what is the use of this thing? You haven't asked me. Is there any use of this dB by dt? Is there any use of this dB by dt? Because due to this, there will be an induced EMF, right? Due to this also, we can have the induced EMF, isn't it? Is there any use? What is the use of this? Tell me, what is the use of this? Basically, I haven't used this one. So EMF is equals to d phi by dt, right? Phi is equals to BA. So dBA by dt, you can use this thing as area dB by dt. Can you? The EMF is equals to area dB by dt. And this EMF will be area. Area of this triangle will be 12 into 5, 60 into 10 to the power of minus 4 into 10 to the power of minus 3. So you will get 7, 6. EMF is equals to 6 into 10 to the power of minus 6. Right? Basically, I have considered only one, wait, there is some modification in the answer. Here in this question, I haven't used this one. This was also there. This is EMF 1, this is EMF 2. So my EMF 1 is this one, and EMF 2 I got this one. So my net EMF is basically EMF 1 plus EMF 2, which will give me 36 into 10 to the power of minus 6 volt. Right? And now if I'll replace here, I'll get 36 into 36 into 10 to the power of minus 12 divided by 6 into 10 to the power of minus 3. So 6, now you will get 36 into 6 into 10 to the power of minus 9, and 36 into 6 is 216. So my correct answer is 216. Did you get it? Very good question. Very good question to clarify your concept. Hi, Kavyan Shukla. On a side note, what are some high weightage chapters I should do before JEE mains? See, for a high weightage chapter, there, like, you can start from the modern physics, okay, dual nature, atoms, nuclei, and then go for the semiconductor. From semiconductor, at least you can expect one or two questions. That current, electricity, kinematics, work energy, power, rotational motion, gravitation. These are some chapters which are the base of the physics. Means if anyone, irrespective of the exam, if anyone is preparing the paper, you will be getting the questions from these chapters, right? So other than that, it particularly depends upon your luck, that on which shift you will get. So my exam is on 24th of Jan. So 24th of Jan, I would be considering that it's a very lucky day. Why it will be a lucky day? Because you have at least two, four papers, right, with you. At least you will be having four papers with you to solve. So tomorrow, which chapter? Tomorrow in the morning, we are having basically what, a mock test. There we will be solving a 25 questions. So I'll select a very best questions. Your exam is on 28th and 29th. Okay. I think that the students who are having exam on 28 little bit, I'm in a doubt that because like if you see the trend from 2023 or 2024, there is a sudden change in the pattern of paper if we got a break in the exam. And generally NTA keeps this in 3 is to 2 ratio or 2 is to 3 ratio. So when we have a gap, and during the first shift after the gap, we see that there is some pattern change. The questions, the type of questions will be coming different from what it was coming earlier. So you have to prepare well, but it was not like ultimately you will get a very difficult type of questions, because I believe that if the paper is difficult, it is very easy to score a very good percentile. See, this exam is about competition. You have to compete with the other persons, right? It's not about that you have to score high. The exam is about that you have to perform relatively better than other person. So relatively, you have to be prepared well as compared to the other. This you have to keep in your mind. So let's move and now solve another question from JEE PYQ. In this, a coil of 200 turns and area is provided to us, is rotated at half a revolution per second. So omega is given to you and they are saying half a revolution. So you know that half a revolution means zero point 0.5 revolution per second. So what is revolution? Revolution equals to 2 pi. So you can multiply 2 pi here. So I can say that it's equal to pi radian per second. Are you able to get that how I have changed this omega? Is it clear, my dear? Right? So now this is clear. Magnetic field is provided to you to the axis of rotation of the coil, the maximum voltage generated. Okay. So we know that there is a generator formula, and from the generator formula, we know that induced EMF is equals to Nawab sine omega t. Nawab sine omega t. And now if I'm considering that for the maximum voltage, I can take this thing as that sine omega t is equals to 1. For maximum voltage, sine omega t is equals to 1. So you can consider this value as 1. Now just substitute the value, you will get the answer. Number of turns is given to us 200. Omega is pi. Area you have to get the area. Area is where? Yes, this is the area. We have 0.2. And magnetic field is also there. Where is the magnetic field? Yes, this is the magnetic field. 0.01. 2.4. So it's 0.4 pi. But we have to find out using this thing. So I'll do one thing, that by 5. So it's 2 pi by 5. And if you compare this with this value, you will get that beta is equals to 5 here. Are you getting this? Are you getting this? Beta is equals to 5. Kavyansh Shukla. Kavyansh, basically, this YouTube channel is primarily focusing on the student uh, who can speak English and who can understand English. So that's why the name is there, Rankplus JEE English. If you want to study in a bilingual or if you want to study purely in Hindi, there are separate channels. Bilingual, there is IIT JEE Rank Plus channel. And if you are a student who understand completely Hindi, that you want me to write the question also in Hindi, then there is a separate channel in Hindi. Okay. Is it clear? Now, shall we move forward for the next question? So you have to bear me. So you are from which state? Guess, a random guess. Can you guess from the dialect? Can you guess? If you guess, if you will guess, then I'll give you one gift. But how can I give you the gift? I can give you, like, I can order from Zomato. Zomato is everywhere, I think. Durgapur, Gujarat. Completely wrong. See, now this question is from 24th JE 2024, 27th Jan shift. It was the first shift. It was the first shift in 2024. I am from Delhi. There is a rectangular loop of length this much, width this much, is placed at 60 degree to the magnetic field of this much. Okay. The loop is removed from the field in 10 seconds. The average EMF induced in the loop during this time, what it will be. Now, you know that EMF is equals to minus of d phi by dt. When I am saying we have to find out change, we can find out using final minus initial divided by the time duration you have. Okay. Now we know that if the loop is removed, we know that finally the flux will be zero. And finally, if the flux is zero, my EMF will be equals to, I need to find out that what is the initial flux divided by time. Now, the time is already given to you, that this is the time, and flux you have to find out using the situations given to you. We have already done one question related to this. Can you? You know that what is phi? Phi is BA cos theta, right? So substitute this. B, magnetic field is this. Area you can find out. I'm writing 2.5 as 5 by 2. Cos 60 degrees is 1 by 2. Time is 10 seconds. One volt. Plus or minus? Plus volt. Are you getting 1 volt? Nani, Delhi. Sir, I know you are from Delhi. You told us in the last marathon. Ah, naughty boy. So you are playing with your sir. I hope that this thing is clear. See, so this question was from 27th Jan shift 1, and similar type of question you will see in 29th Jan shift 1 in JEE 2024. See, in this question, there is a square loop of side 10 centimeter. In square, we have all the sides equal. Resistance is 0.7 ohm, is placed vertically in, see, vertically in east-west plane. vertically in east-west plane. If I'm having a table here, and in this table, on this table, I'm drawing there is east, there is west, there is north, there is south. Okay. And in the east-west plane, I'm keeping a square loop. That means that this is the square. If this is the square, now you have to find out a uniform magnetic field is also provided to you in northeast direction. So northeast direction, that means this one, that the magnetic field is moving in this direction, 0.2 Tesla. So the angle will be 45 degree. The magnetic field is decreased to 0 in 1 second. So here see the pattern. They are saying that the magnetic field is decreased to 0 in 1 second. I know that if the magnetic field becomes 0 in 1 second, then what does it mean? It means that the final flux will be 0. If the final flux is 0, I can easily find out that induced EMF will be, and here one, the best thing is that my time is also 1 second. So I can say that my flux will be equals to d phi by dt, and phi here you can find out be a cos theta, and time is 1 second, right? Cos is what, 45 degree here. So magnetic field, what is the like, there is no use of this resistance in the question. There is no use of the resistance in the question. So now you can find out that Tesla is 0.2, area is 100 into 10 to the power minus 4, be a cos theta. Theta is 1 by root 2. So you will get root 2 into 10 to the power of minus 3. So this is what you will get. Is it clear, my dear? Are you getting this as your answer? Please do let me know. Are you getting this? Now let's move to the another question. Now this question. A horizontal straight wire of length 5 meter is extending from east to west, falling freely at right angle to the horizontal component of the Earth's magnetic field. Okay. Now, somebody will say that Earth's magnetic field is not in the syllabus, but there is a question from Earth's magnetic field in JEE 2024. In JEE 2024 also, the Earth's magnetic field was not in the syllabus, but at least you must know a basic criteria that how you are going to solve this, right? Now, on 29th January shift 2, there was a question. You have to find out that what is the instantaneous induced EMF in this wire if the velocity is this much. I know when the wire is moving, the induced EMF is BLV sine theta, right? This is the only formula which I am having. Now, it is provided already to us that there we are considering the horizontal component. If we are considering the horizontal component, I do not need to consider the angle because it's already been provided. Simply you have to put all the values which is there. The magnetic field value is 0.6 into 10 to the power of minus 4. The length value is 5. The velocity value is 10. Multiply it by 6. 6 5 is 30 into 10 to the power of minus 4. EMF. See, many a time you will get these types of scenarios in which you have to arrange these patterns like this. So you will get 3 into 10 to the power of minus 3 volt. The answer is 3. Are you getting 3 as your answer? How many of you are getting 3 as your answer? Is it clear, my dear? Okay. Now, let me show you one thing. Okay. Now, in this class, we have completed the Faraday's law. We are done with the induced EMF and the current. We are done with the Lenz law. These tools are pending. Eddy current, self, and mutual induction. I'll take in a like tomorrow's class. I'll take questions from this eddy current and the self induction current. I have another class on a different channel, so I'm winding up here only. Okay, so in the next session, I'll take the questions from the other topics. Okay, I'll write it here. This will be in the part 2. I hope that you enjoyed today's class. There are some questions in this PDF which you can refer if you want to do practice. Remember one thing, that your limit is always in your mind, it's not in the reality. And you know that limits are always crossed in the end. Think of like a hero in any movie, you will see that they are performing their best performance in the last part. So this is what is expecting from your, that these are the last 10 days where you have to perform well in your academics. And if you face any issue, you can call me. There is an assistance which you can take, right? And also I can tell you one thing. I have to tell you one thing. Wait, I forgot to consider. I have already taken a formula session, so you can watch that formula session also. This thing. If you are facing any issue in your preparation, you can do one thing. You can get personalized one-to-one session with me. To book this session, you have to download Rankplus app. After downloading Rankplus app, there is an option to select the teacher, and selecting me as your mentor, Manoj Kumar. You have to pay, like if you want me for one session only, then you have to pay 499. But if you think that there are so many doubts which you have, you want to take more sessions, then there are discounts which is going on. To book 10 or more sessions, the fees is only 199. Okay, so download the Rank Plus app, and I'll see you in my one-to-one session later on. Okay, so now we will meet again. Bye bye. Have a nice day. Yes, good night, everyone. And to book the one-to-one session with me, you can download the Rank Plus app. After downloading the Rank Plus app, you will see their options of personal mentorship. You have to select Manoj Kumar as your mentor. Then you can book the session as per my availability. Okay, so till then,